Hi guys! So on the last video I did, this slide cut off, so I'm going to go ahead and rework it all, and then we'll get on to colligative properties, which is our next topic. Okay, so recall that molarity is moles per liter. Okay, so when we're finding molarity, we need to make sure we have moles, we need to make sure we have liters. First thing you need to note is what we have. I've got grams, which I can find moles with. I've got kilograms, that's for molality, and I've got milliliters. Okay, so first thing I'm going to do is get my grams to moles. And I've got 24 plus 6 plus 32, so we're looking at 62 grams. And I've got, yes, 0.277 moles of our ethylene glycol. Okay, once I get that, I can do molarity. So it's going to be 0.277 moles over 0.515 liters. Okay, don't forget milliliters is going to have to be converted to liters. So my total molarity is 0.539. Okay, so there's A. B is molality. Remember, that's moles per kilogram. I already have moles, and it gives me kilograms. 277 moles over 0.5 kilograms. And for sig fig purposes, just remember that you need to keep the least. Both of these have 3, so we're keeping 3. I get 0.554 molal. And then C is mass percent, so we're looking at our masses. We don't have to use moles for this one. So I've got 17.2 grams. Remember, it's solute over solution. So don't forget, kilograms has to go to grams. So this is going to be 500 grams because half a kilogram is 500 grams. And on the bottom, I'm going to need to add them together. The solution is the solute plus the solvent. And don't forget to times it by 100 because it's a percent. And I get 3.33%. Okay, mole fraction is very similar, but we're doing it with moles. Okay, so I've got the moles of the solute, and I need to convert my 500 grams to moles. The molar mass of water is 18. So this is 27.8 moles of water. Don't forget, for percent and moles, either fractions or mass, you have to have the total solution on the bottom. I'm just going to do 1 for the whole thing. So I've got the 27.8 plus the 0.277. I get 0.00986. And then for E, all I do is times that by 100. And I get 0.986% for moles. Okay, again, if you have questions, please reach out. Make sure you fill out the survey for office hours so I know when the best time would be. But as always, you can send me an email and I will get on if I can. Okay. So it's going to go through it all. If you need more practice, you should absolutely work this. And then if you need help with it, let me know and we can get on and go through it. Okay, this one is also a little different. So they only gave us one number and they told us what glucose was. And they want to know the molarity, and they gave us the density so we could get to volume. So remember that mass percent is mass of solute over the mass of the whole solution. So we can break that if we need to, because remember, a molarity is moles per liter. Okay, moles of solute over liters of solution. So I can say that I have 6.56 grams of glucose and 100 grams of, really it's solution, it's not. Okay, because that's what a percentage is. 6.56 grams out of 100 is the 6.56%. So the solute I need to get to moles. The molar mass of glucose is 180. And if you need help with molar mass, let me know. We will absolutely talk about it. Okay, so there's our moles of solute. To get grams to liters, I have to use the density. So the number always goes with the first unit if there's a slash, so per. Don't forget, you don't want milliliters, you want liters. Okay, I get 0.0971 liters. And then all I have to do to get molarity is I divide the two. And so for molarity, I get 0.375 molar is that solution of glucose. Okay, this is really the worst kind because it asks you to take one number and separate it. There's not going to be any like this on the quiz or the test. Okay, sorry, my little recorder is blocking the bottom of it, so I couldn't see what the answer was. We'd already worked it though, it was fine. Okay, next topic. This is really for the beginning of week 2. We're looking at colligative properties, and those are properties that depend only on the number of particles, not what they are. So it depends only on the number, not what they are. Okay, so a good example of this is going to be like sand versus salt on the highway bridges when it gets really cold out and we're preparing for the winter mix. Okay, it doesn't matter what it is, it does matter how much of it we put down. Okay, so this is going to be a super important equation. Notice the small m, that's molality. Okay, the Kf should be given to you. If not, you would have all the other pieces and you'll solve for the Kf. Okay, and then the change in temperature, that's how much below freezing we're going to be. Normally, if it's water, we're talking a negative number. Okay, so just remember that water freezes at 0 Celsius, so that's normally our initial is 0 Celsius. Okay, here's just a table of freezing and boiling constants. You may need to note this slide down for your homework. On the test, I'll make sure to give it to you or the quiz. But on the homework, they don't. So make sure you have this ready or you can go back and pull it up. Okay, so what's the freezing point of ethylene glycol solution? I do want y'all to note that normally we're dealing with water. So this is the main values we're going to use because we're only going to use water. This one is freezing, so we're using the Kf, not the Kb, because Kb is for boiling. So I'm going to write Kf is 1.86. Remember, that's degrees Celsius per molal, small m. And remember, our delta T is equal to our Kf times m. So we've got Kf, 1.86 times 1.7 molal, which it gave us, but it won't always give it to you. You need to make sure you're prepared to solve for molal first And I get that the change in temperature is 3.16 degrees Celsius because my molals cancel out. So the freezing point is not 3.16. Remember, TF, delta T, is equal to final minus initial. Remember, our initial is 0 because we're talking water, which means that the freezing point is actually going to be negative 3.16 degrees. Just remember the freezing point, it's called the freezing point of depression, so you need to keep in mind it should always be below 0 because we're bringing it down. That's the whole point of these colligative properties, and that we're adding things to our solution. So we're bringing the freezing point down from its normal value. It's the same thing with the boiling point. We're bringing the boiling point up. Okay, so the boiling point equation is the same. This is called boiling point of elevation, so it goes up. The only difference is you're using KB instead of KF. Also, temperature will be above 100, so it should be a positive number. Okay, it tells us boiling 100. It tells us the change in boiling point is 5. So remember, we've got our delta T is equal to KB times M. And our KB, this is from the table from before, is 0.512. Okay, you won't be expected to memorize that. Again, I'll give it to you on a test or a quiz, but on the homework, you will need to find that slide. Okay, and it tells me the change in boiling point is 5 degrees. And I've got my KB at 0.512. And I'm looking for the molality. Actually, I'm looking for the mass, but I need to go ahead and solve the rest of it. So to get molal by itself, I'm going to do 5 divided by 0.512. So I get that the molal is 9.77. Okay, and remember molal is moles per kilogram. But the kilogram they gave me was 1, which means 9.77 molal is the same as 9.77 moles in this scenario of our ethylene glycol. And then I've got to solve to mass because that's what it's asking for. And this was 62 grams. We did that mass earlier. I get 606 grams of our ethylene glycol, which is a whole lot, but changing a temperature by 5 degrees is also a lot. Okay, they did put it in scientific notation. They were paying more attention to sig figs. Okay, mastering chemistry will tell you if your sig figs are wrong, and so just make sure if it notes it, just change it. It's not going to take off very much. Also, they put it in scientific notation. This is the same as 610 grams. And you can put it either way into mastering chemistry. It'll take it just fine. Okay, osmosis. I'm not going to test osmosis, but it's a good thing for y'all to know. Most of you've taken biology already, and so you know about osmosis. But remember, that's the flow of a solvent from a solution of low concentration to high concentration. From low to high is what osmosis is. And there's generally that semi-permeable membrane that allows the solute to stay on one side, but the liquid flow goes through. There's also osmotic pressure. Again, I'm not going to be testing this. This value, though, for R, just hopefully you remember your gas laws when we did PV equals nRT. Those are coming back in chapter 15. So this R is for gases, which is why we're talking about pressure. Also, just remember, temperature should be in Kelvin when we're using R. Okay, and then the big M is molarity. Okay, so they're going to go through a problem. All they do is plug everything in. So we're looking for molarity, R, and temperature in Kelvin. So we got to find our molarity. That's what it's asking us for. We've got our pressure, but remember R is an atmosphere, so you've got to convert. Okay, it told us 25 Celsius, which is 298 Kelvin, and you just do some algebra and solve. Okay, the Van't Hoff factor, this is if a particle breaks into more than its pieces. So like something like calcium chloride. Okay, there are 3 ions there. It's not just, so it's breaking more. Okay, so it's Van't Hoff factor, that's the ratio of moles of solute to the moles of dissolved unit. So like this breaks into calcium and chlorine, but 2 chlorines. So there we're looking at particles in solution would be 3, moles of formula unit would be 1. So in this scenario, we'd be looking at 3 would be our Van't Hoff factor. This is also something I'm not going to test like number-wise, but you need to know the gist of it. So here, they're not always the same as what we expect because the calculation isn't as easy as the one we just did, but it gets you pretty close. So here, oh, actually, calcium chloride's the example. So remember the Van't Hoff factor is I, and that's 3 because there's 3 particles into 1 ionic compound. Okay, so they're going to use this calculation and they're going to plug it in front of molarity. Now again, I'm not going to ask this, but it's the same thing as we were doing before with the KF and then molality. You just need to plug in that Van't Hoff factor into it as well. And here's just some examples of colligative properties in the medical world. Okay, so isomotic or isotonic, that means it has the same pressure inside and outside. And that's healthy red blood cells. Those shriveled red blood cells are called hyperosmotic or hypertonic. That means there's higher pressure than the solution inside the cell. Okay, so the net flow will be out of the cell, which makes them shrivel up, which of course is not good. Same thing with those swollen red blood cells. We've got hypoosmotic or hypotonic, and that means there's lower pressure on the inside of the cell, so it flows into the cell, making it swell up, which is also not a great thing. Okay, so that is it for chapter 13, and I'll be posting chapter 14 soon. Y'all have a good day.